All right, so hi everyone. Thank you for joining today. My name is Nathan Piccini, and I am the marketing manager at Data Science Dojo. Um, just so everybody knows, and I've kind of been talking about it a little bit already, we do have a raffle that we've just released the link to, and my team will be posting it every so often, just so that everyone gets a chance to join it. In that raffle, we're going to be giving away 5 ebooks of R for Everyone, and also 1 ticket to the 2022 New York R Conference. And that ticket would be virtual or in person, depending on what the winner decides they want to receive. And we will be doing Q&A kind of throughout the presentation today. We'll be stopping intermittently for it. So if you have any questions, please use the Q&A tab if you're on Zoom. It helps keep us organized. And if you're on Zoom, you can also upvote questions that you like or questions that you also have. And then if you're on our live streams, we have team members there who will take your questions and put them in Zoom for you. So please, ask your questions. Jared's here to help answer them. So with that, I do have Jared Lander here with me today. He is the Chief Data Scientist at Lander Analytics and also the author of R for Everyone. And today, he's going to be comparing some tree-based models for us. So Jared, why don't you go ahead and take it away?
Hi, thank you very much. Very happy to be here, and welcome to everyone tuning in from all around the world. I saw we had people spread out everywhere, and that's always awesome to see. So thank you, those of you who are bearing the different time zones. I know that could sometimes be problematic. You're waking up really early or staying up really late. So thank you for being here. We are here to talk about tree-based models and everything that can encompass. There are so many different types of trees. There are really many types, and we'll cover a bunch of them. Not all of them, but a good amount of them. So our plan for today is we will see a little bit of math, just a few equations, not too much, just the basics. And we will see how to train the models, and we will also compare their speed and check their accuracy, and we will visualize the trees when possible. And finally, we will look at a unified interface for all of them. Feel free to ask questions as we go along. There's some natural breaking points in this show, and as I get to the breaking points, I'll check questions. So first up, we have to look at the data, because in order to have data, in order to do any of these algorithms, you need the data. And we will be looking at credit data. And if you want to get access to this credit data, there's a package in R called model data, and you could use the data function to extract the credit data from the model data package. And that's credit underscore data, comma, package equals model data. That's one line of code that is not in this talk, how to actually get the data, but is available as an R package. And this is just a data set about credit worthiness, and all reservations about credit scores aside, let's say you're deciding if you want to give someone a loan, you want to determine if they have good or bad credit. And so we have this data set with prior labels on people's credit as good or bad under the status column, and it is our goal to predict whether it's going to be good or bad. Now, we're doing a binary outcome today because 90% of the AI tutorials are all binary, right? But of course, we could do so much more with trees and many other algorithms. But with trees, you could do binary outcomes like we're doing, multi-class classification, numeric outcomes, which is regression essentially, but you could do a regression tree. You could do Poisson outputs where you have count data. You could do survival models. There's all sorts of different types of models you could use as for your output. You could do different types of outputs. But today we will focus on binary just because it's well known and it fits this problem well. The inputs to all of our tree models can be either numeric or qualitative in some form. And when I say qualitative, I mean multi-class. The multi-class can be many different types, binary or 3, 4, 5 classes. And there could actually be other types of inputs. Those are more edge cases. So give me 1 second just to make sure nothing's beeping at me here. And we will look at our outcome variable. If we do a simple count of the outcome variable, how many good, how many bad we have unbalanced data, or imbalanced data might be the better word. And some algorithms handle this just fine, but usually for classification models, it's better if you have balanced data. So I will turn to the recipes package, which comes under the tidymodels framework, to prepare my data set. The first step I'm going to do is convert strings into factors for our status variable or outcome variable. That's just going to be what I'm doing here. You'll see later on, we'll be using repeated recipes. Sometimes I'll make sure the outcome is a factor, sometimes I won't. The key step here, though, is themis : step _ upsample. In this case, what I am doing is I'm taking my minority class bad and upsampling it. So it's sampling with replacement. So we have a balance between good classes and bad classes. I had to convert the status to a factor in order to use the upsampling, and then I changed it back to a string for use later. To do upsampling or downsampling, depending what you want to do, the best way to do it as of right now is the themis package, which is an offshoot of the recipes package. It's called themis because themis is the name of the Greek tidiness of order and fairness. So that's why they named the package that way. And what we're doing right now is making sure we have roughly the same amount of good and bad outcomes. This way, our algorithm doesn't just go, hey, if I guess good every time, I'll be right 90% of the time. So that's to balance our data. And we were to plot it again. After upsampling, we now have equal numbers between bad and good. Let's start our show with single trees, individual trees. Let's say this is our data set. We have 2 numeric inputs. Of course, we could have many numeric inputs and many qualitative inputs, but just for visualization, we have 2 numeric inputs, and the color of each dot represents our qualitative outcome, which is what we're working with today. It's a 2-class binary outcome. Bluish green for good, red for bad. And the idea is that we want to break up this space into a bunch of regions that separates the good from the bad dots. We want each individual region here, and there are 2-dimensional regions because we have 2 inputs. We want to break it up so it's as many, each region has mostly good or mostly bad. Roughly like this. Here we have what looks like 1, 2, 3, 4, 5, 6, 7, 8 separate regions. Actually, maybe 7 separate regions. The exact number doesn't really matter too much here. But these lines, these black lines, and I'll use my mouse to hover over them, represents where we're dividing the space up. I got a little confused because of this line at 0. I wasn't sure if that was a dividing line or not. But you see here, we have this region, which is everything here will be labeled as good. And this region, it's greenish, so that's going to be mostly good. And this pinkish region here would be mostly bad. It's a little hard to visualize this, especially the way they're all blocky, but the idea is that within each region, you want as many of either good or bad as possible. And the majority rules in a region. So if we have a binary outcome, if you have 10 points in a region, 7 are bad, you declare any points that you're predicting in that region to be bad, or 70% bad even. If this were a numeric outcome, you would take the average in the region. This is represented here for a classification. So the prediction for a given region, for a class, is essentially just the percentage given that class. This is 2-class, but it generalizes to multi-class. Basically, it's a vote. If you have 4 classes, you would say you would count the percentage of each class in a given region. Okay, so for region M, what is the majority class? If we had a outcome variable, continuous outcome variable, instead of taking a majority vote, you would just take an average vote. So you're given a new point you want to make a prediction on, you find out which region it belongs to. That's this indicator. X is a subset of a certain region M. If row X falls into this region, take the average for that region as prediction for row X. That's the general idea. Again, averages for continuous outcomes, votes for categorical outcomes. That's the general idea underlying how we will make predictions. Before I continue about rpart, I'm going to pause for a second just to see if anyone has questions about the concepts or the math or what our goals are. I'll just pause and give everyone a moment to see if they have questions. And if not, I will continue on with the talk and start showing how to fit these models using R. So there's a question, does feature scaling have any effect on tree-based models? Typically, no, you don't need to. Most tree-based models, at least the ones I'm going to be talking about, you typically don't need to scale the inputs. And by scaling, I will assume you are referring to subtracting the mean and dividing by the standard deviation. You shouldn't really need to do that for tree-based models. It doesn't mean you can't do it, but you typically don't have to. Another question is, do I have any resources to review the math concepts? Yes. I'm just looking up on my bookshelf right now. I'd say my favorite book for this is The Elements of Statistical Learning. And if you're not as into calculus and matrix algebra, there is another book by two of the same authors, Introduction to Statistical Learning. I think between those two books, you'll have a really good grasp about the math behind these tree-based algorithms. I'm just looking at my bookshelf here to see if any other titles strike me. I'd say those two, Elements of Statistical Learning and Introduction to Statistical Learning. I really like both of those. I personally am really into the math, so I like Elements a little bit better because it uses matrices instead of non-matrix math and has a little more calculus. That's my thing. But the cool thing about Introduction to Statistical Learning is that for people who don't like as much math as I do, it uses more summations than matrix algebra, and it has some R code in it, which is always fun. Okay, so let's fit a single model. And one of the first packages to do this, I was going to say one of the first packages in R, but one of the first packages in any language is rpart. And this stands for recursive partitioning. Because when you're actually fitting a tree-based model, we like to think of it as a tree of branches, but you're really, if you go back to my diagram, you're recursively splitting up the input space into more and more rectangles. So you're recursively partitioning the space. So rpart. It could do regression, classification, Poisson, and survival models. And again, Poisson, and I know I'm pronouncing Poisson incorrectly. I have a horrible time pronouncing French words. That is for count data. Now, the only interface for this, as we'll see in a minute, is a formula interface. That's going to be important later. Categorical inputs can be treated either as a character or a factor. A character just being text, and a factor essentially being like a normalized database. It's a way of sort of creating the dummy variables in the underlying data structure. We can get into that. If you have a categorical outcome, our binary outcome, you can store that either as a character or a factor. And this handles missing data for us by using surrogate variables. So we have no need to do any imputation. We actually fit the model by calling rpart, that's the name of both the package and the function, and we give it a formula like we would for a linear model. And we say outcome variable tilde dot. The dot in this case is a shorthand for saying all other variables. Right? I could say status tilde variable 1 plus variable 2 plus variable 3, or since I'm using all of them, I just say dot and be done. So nice and easy to fit the model. It's pretty fast. To visualize it, instead of using a built-in visualization, I'm going to use the rpart.plot package, which has the eponymous rpart.plot function. I give it the model, and it shows me the tree-based visualization. This is all the defaults. I haven't customized it, and you can highly customize this visualization. But I just use the defaults to keep it simple. And this shows you a branching display. And for simple trees, this is very easy to understand. You first ask the first question, is seniority, which is one of the variables, less than 4? If you say yes, you turn left and go down that branch. If you say no, you turn right and go down that branch. That's simple. Let's say we went left. We then ask the question, do you have records? Whatever that may mean. Yes, well, then you have a 11% chance, no, I want to get this right, a 13% chance of having good credit, meaning you have I'm trying to do basic math in my head right now, a 87% chance of having bad credit. So it labels it as bad. If you had said, no, I don't have records, then you ask another question. Is your job one of freelance, others, or part-time? If you say yes, you have a 29% chance of good credit. If you said no, you ask another question. Are your assets less than 1,000? If your assets are less than are your assets greater than, less than 1,600, I misread it. If you answer yes to that, that's are your assets, or is the amount of your loan greater than 1,100? And you ask these series of questions. And we went back up to the root node, the top. We then ask about records again. If you answered yes, it gives you bad credit, well, labels you as bad credit. If you had answered no, it'll ask you another question. So it's asking a series of these questions, which for a simple tree is explainable. But once you get into a complicated tree, it becomes a lot to ask. One cool thing for those of you used to linear models, you could treat the node, the leaf node all the way at the bottom, as an interaction term. It's an interaction between all the previous variables asked about it. That's one way to visualize this. A more summaristic, which I know is not a real word and I just came up with it, but a more summarizing view is a variable importance plot. Now these can be defined differently depending on your type of model, but for a rpart model, the bars represent the sum of the goodness of split for each time a variable is used, because a variable can be used multiple times. This is telling you how much it improves the model each time you split with that variable. In this case, seniority is the most important. Now, important, what does that mean? It doesn't tell you if it has a positive effect or a bad effect. It's how much influence this variable had on the model fitting. It doesn't tell you whether it had a negative influence or a positive influence, how much of an influence relative to the other variables. So in this case, seniority, records, job, expenses, age, and so on are the important ones. Now, like any good tree-based model, there are a number of hyperparameters or tuning parameters you can control. The main one to me is max depth. It is a maximum number of splits for your terminal nodes. That is how deep and complex the tree can get, because the tree can very quickly overfit if you have too much max depth, and it can really underfit if you don't have enough depth. It's not saying it has to go this deep, it is the maximum it can go. There are these other parameters like min split, the minimum number of observations in a node for a split, and min bucket, but max depth is really the one you'll be controlling most. If you want to change the parameters, you need to pass them to the rpart.control function, which you pass to rpart. Well, we'll worry about that for now. I'll take a moment for some questions. There's a question about, what about smoke for sampling, for upsampling and downsampling? People are big fans of smoke. It's great. I find for most of my case, either upsampling or downsampling works just fine, and I don't need to bother with smoke, but smoke is great. There's a question about the bar plot, the variable importance plot. Does it show coefficients? It shows feature importance. I would hate to call them coefficients, because to me, the definition of a coefficient is a multiplier. It's how much you multiply a variable by to see how much it impacts the outcome. And that shows you the importance, how it affects the model fitting, it's not a multiplier. So I wouldn't want to call it a coefficient. There's a question, can you influence the decision percentage of the tree? The default algorithm splits the division of the first node 50-50. I don't think it has to split at 50-50. I think it might just happen that way. It doesn't need to be a 50-50 split. It needs to be a binary split, yes or no, but it doesn't need to be 50-50. And with these tuning parameters, you can control sort of how things are split. I hope that answered your question. But why should we fit just one tree when we can fit multiple trees, such as a random forest? This is fitting many trees. And this is originally came up with by Leo Breiman and Adele Cutler. The general idea is that you fit capital B independent trees, each one randomly built. Okay, we'll talk about the randomness. You fit a bunch of randomly fit, independently fit trees and average them together. This is called bagging, bootstrap aggregating. It's a random bootstrap and you have random variables. And a bootstrap is when you resample your data with replacement. we're going to start with the randomForest package, which was written by Andy Liao as a wrapper around Leo Breiman's original Fortran code. Now, this can handle regression or classification. It has two interfaces, a formal interface like we saw before. And if you're going to use a formal interface, your categorical input data must be stored as factors. And your outcome variable, if it's classification, must be stored as a factor also. You also have an XY interface where you have your input variables X, and it must be a dense matrix. And you can have an output column of Y, and if it's classification, it must be a factor. And it does not handle missing data for us. You would need to impute your data. So to do this, we will use recipes for setting up our model, for setting up our data, actually, not our model. So we say our outcome variable status, and we're going to use everything else as an input. We are going to impute all of our predictors, our inputs, and we will make sure that all the strings are converted into factors. And this will give us a data frame that has factor variables and no missing data. We can then call the randomForest function, which is just randomForest of a capital F, and give it the formula, status on everything else. And the data set is that imputed data set we created with recipes. And if we want to plot this, the default plotting interface shows us the error rate with the number of trees. And you can see it levels off. As you fit more and more trees, it just sort of peters out. You don't get much more accuracy from that many more trees. We can also show a variable importance plot. In this case, it is how much each variable contributes to increases in accuracy. Because remember, we have hundreds of trees, each of which is doing multiple splits, which we will talk about in a second. So each variable can be used many, many times. So we get a chance to see, hey, how much are these variables contributing to the accuracy? And even though they say like you don't really need to tune randomForest, there's a lot of ways we can tune it. So let's talk about why it's called a random forest. So the first is, how many number of trees to grow? 100, 500, 1,000? That's a good tuning parameter. That's traditionally considered, hey, the only thing you really need to tune. Well, traditionally. Then we have m_try. Now, randomForest, you might ask, hey, if you fit 100 trees, won't it just fit the same tree each time? Well, there's two levels of randomness in a randomForest. The second is m_try. We'll start the second. Within each tree, when you're building the tree, you have to make multiple splits. And each time you're going to split in a traditional tree, you search all the variables to see which will give you the best split. With randomForest, you say, hey, if I have 10 input variables, I want to make a split, randomly choose 4 of them, and out of those 4, decide which is the best. You ready for your next split? Randomly choose 4 variables, decide which to make your best split. Choose another 4. That's one level of randomness. The other level of randomness is sampling the rows. For each tree you're going to fit, instead of using all the rows in the data set, you will use some subset of the rows. So you have 2 levels of randomness of randomForest. You're randomly selecting the rows to fit the next tree on, and you're randomly selecting which variables to consider when choosing how to split your data. So that's how, out of your 500 perhaps trees, you make sure they have 500 different trees, then you can average the results together at prediction time. I'll pause for a moment to take some questions. The question we have right now is, in case of many categorical values, would you suggest to one-hot encode them, or should they be left as is as factor variables? That's a very interesting question. So for models like randomForest, you have your choice. Other models, you have to do either just factors or just one-hot encoding. The question is, which one is better? So Max Kuhn gave a talk a few years ago at the New York R conference, which is what we're giving the ticket away for, New York R conference. And he gave a talk about when to make dummy variables and when not to. And his end result was really meh. It depends on the type of model you're fitting in on your data set. So there's no clear-cut answer. Should you leave them as factors or should you not? So it's really tough to say. Check out, go to a plug for the New York conference, rstats.ai. Find the video from Max Kuhn from like 4 or 5 years ago, and he talks about it there in depth for 20 minutes. There's a question, why do R and Python implementations of random forest vary that much in terms of results? Well, first of all, it depends which random forest package, because even in R, we just saw random forest, we're about to see Ranger, and there's going to be other random forest packages as well. Python, are you talking about scikit-learn or some other package? The random forest package in R uses Leo Bryman's original Fortran code. Ranger uses custom C++ code. Scikit-learn uses gradient descent. So they're all different ways of fitting the model. So not only do you have two levels of randomness in the number, which rows you're sampling and which columns you're sampling, you also have different implementations of it. So none of these methods are the same, right? So you really just got to try a bunch and see which one gives the most accurate results, however you're defining accuracy. So let's talk about Ranger, as we just said, because this is a fast implementation. Not that Fortran wasn't fast. This is considered faster than the random forest package, and it's written in C++ underneath the hood, though we will use it from within R. This can do regression, classification, and survival models, has both a formula interface and an input-output interface. The formula interface, your input variables, if they're categorical, they could be either character or factor, but if there's classification, the output must be a factor. If you use the XY interface, your inputs can be dense or sparse, and your Y, if it's categorical, it must be a factor. You also have a third interface, a data frame interface, and you say, hey, here's my data frame, which column is the output, and then the rest are inputs. And this does not handle missing data for us. We would need to take care of that. We already took care of that before, so we use the same imputed data. And then we call Ranger, which is both the name of the package and the function, give it a formula, outcome tilde dot for all the other input variables. And we say data is credit imputed, our data set that we imputed earlier, and importance equals impurity, which will help us with the variable importance plot later. We could use Ranger to fit a single tree, but that would defeat part of the purpose. If we try calling plot on this model, there is no plotting method. So you get this error saying no plotting for you. There might be other ways to get plots out of Ranger, but not using plot. You can, however, get a variable importance plot, which is giving us different results than random forest. Because this definition is actually kind of similar, though, how much each variable contributes to increases in accuracy. And just like before, yes, why does R and Python give different results? Here, random forest and Ranger and R give you different results. Right? Lots of levels of randomness and different methods of implementation. Now, again, even though you're not supposed to have to tune a random forest model, here we go. Lots of different tuning parameters, the number of trees to grow, the number of candidate variables to check at each split, how deep any individual tree can get, whether you should sample rows of replacement, how many rows to sample, and you have regularization, and rules for splitting the variable. Lots of ways you could tune this thing. All right, I'll just take one more moment while I put the bottle away to wait, and we can continue. But all the code you're seeing here should be runnable. But I know I didn't put in here how to get the data set, but I told you data, data parentheses, credit underscore data, package equals model data in quotes, and you can run all the code here as is. Okay, but now let's turn to boosted trees. We are going to stack the trees. We're not going to have just one tree. We're going to have hundreds of trees, but instead of them being independent, they will all learn from each other. So this is a very glossy equation. We're going to gloss over it. Basically, when it comes time to make a prediction, that's y hat, for an individual row I, assuming we fit t trees, right? We are just going to make a prediction by making a prediction for each of the individual trees and summing them up. Now, depending how you view this, you're either making predictions for individual trees and averaging them, or you're making predictions for, let me take that back. There are two ways to think about making the trees, because each tree is getting better based on the previous trees. You fit a tree for a model. And technically, by the way, it doesn't have to be a tree. It could be any model. Boosting works for any type of model. It doesn't have to be a tree. We'll get back to that. Let's say you fit your first model. You then, for your training set or your test set, if you have, you want to see how well you fit your model. So you look at the residuals. And I see this question about residuals. Residuals are also called errors. It is how off your predictions are. You fit a model, and then you make predictions using the data you fit the model on, and then you say, hey, here's my true value for my y's, here's my predicted values, how wrong am I? And now you have 1,000 rows, each one has a measure of how wrong or correct it was, that's the residual. And then you fit a second model based on that first model. And the way you do that is by saying, adjusting the row weights. So models with large residuals, which means you got them wrong, get a higher row weight. Rows with smaller residuals, meaning you did well in those rows, gets lower row weights. Okay. Then you fit the next tree weighted by these row weights. And that allows you to pay more attention to rows you didn't do well on and less attention to rows you did well on. That's one way of adjusting the trees as you go. The other way is just on your second tree, instead of fitting the tree with the original outcome variable as its outcome variable, you're using the residuals from the first model as the output variable for the second model. So it's really allowing you to see how well it's fitting. And you do this repeatedly. You fit another tree based on how well or how poorly you did on the second tree, then a fourth tree and a fifth tree and a sixth tree, each getting better based on the previous trees. And there's two ways to think about this. If you're fitting each subsequent model by having row weights based on the residuals from the first model, then you can average the predictions at runtime. Or if each subsequent tree, you don't deal with row weights, but your outcome variable for the subsequent trees are the residuals of the previous tree, then when you make a prediction, you sum up the predictions for all of the individual trees rather than averaging them. I know that got a little hairy in there, and I apologize. That got a little messy for the different things. This is much easier of a whiteboard I could draw on than that. The basic idea is each tree learns from the mistakes of the previous tree and tries to get better. And whether you're using trees or any other type of underlying model, the idea is to have a bunch of simple models that you're sort of stacking together. That was a bit complicated, so I'll pause right now for some questions. There's just a clarification question about residuals. Yes, residuals is your actual outcome variable minus your predicted outcome variable. There is a question about if my residual has a higher number, is there a way to transform it, or how can it handle it? I'm not exactly sure what you're looking for here, but the idea is that if you have a high residual, that means the subsequent model in the boosting. So remember, residuals are row by row. So if you train your model of 1,000 observations, you'll have 1,000 residuals. And then what you do when you fit your second model, whether it's a tree or other type of model, you are going to weight your rows, your case weights, by those residuals. So a big residual for a given row just means pay more attention to this row during the next model fitting to make sure you really get it right. So you wouldn't want to transform it or handle it. You're using that to tell you, hey, I didn't do well in this row, pay more attention, do better on this row in the next model. And if you fit 1,000 models, each one getting better than the previous one, your model gets better and better. There are a few packages to do this. The first one we'll look at is GBM. This is the original gradient boosted machine. And it works with different models, the most notable being tree models. It also works with linear models. But we'll stick to trees. This could do regression, classification, Poisson, and survival and ranking models. Now it only has a formula interface. That's a bit of a half-truth. There's a helper function called gbm.fit, which can use the XY interface. We're just going to talk about the main entry point to the package, which is a formula interface. The categorical inputs must be factor variables. And if your outcome variable is binary, it must be 0, 1. And it handles the missing data for us through the use of surrogate variables, which is very nice. So to do this, we have to use a recipe to prepare our data. This is pre-processing or feature engineering, if you will. We will make sure that our outcome variable status is an integer that's 0, 1, 0 based, and that all of our strings, our characters, are factors. We then fit a model. To do this, we have this familiar formula interface, GBM, name of the package and the function. We say status tilde dot outcome variable tilde all the other variables, pass it our data set, and our distribution is Bernoulli, our outcome variable. The distribution is dependent on what your outcome variable is. If it was a numeric, it'd be Gaussian. If it is two-class, it'd be Bernoulli. If it were multi-class, it'd be multinomial. I think they use multinomial, don't quote me on that for this package. If it were count data, it'd be Poisson. And by default, and we're using the default number of trees, 100 trees, means you're gonna have 100 trees, each getting better and better. To plot this, the default plot is a partial dependency plot. And that's a bit ambitious here. In this case, we have the seniority variable on the x-axis, we have the income variable on the y-axis, the two panels, no and yes, are the records, whether or not you have records, and the color is the prediction, which is kind of hard to see. It's kind of a bit messy. So sometimes plotting too much doesn't really help you. Thankfully, we have the variable importance plot, which tells us the relative influence of the input variables in reducing the loss. So we can see here that income was the most helpful for getting a better model, followed by seniority, then records, then type of job. There are a bunch of tuning parameters here, like in trees for the number of boosting rounds, the interaction depth, which is the maximum depth a tree can get in terms of the number of interactions, and then the n dot min. I think I might have too many things here, but min knobs in node. Minimum observations in a node, that is one thing. How much you're going to shrink, that's the learning rate, and the bagging fraction, percentage of data to sample at each round of boosting. Because much like random forest, for each tree you fit, you can randomly sample the data. That allows you to say, hey, don't use all the data. It's a form of regularization. It's a form of preventing overfitting. Speaking of which, there's a question. If we're giving more attention to higher residuals, are we not kind of overfitting? Yes and no. So as you get to higher residuals, rows that had high residuals, as you tune to them, their residuals will eventually get small. So for subsequent trees, you'll be paying less attention to them. So as your trees keep going, the residuals for rows at each tree will get bigger and smaller as you go. But yes, overfitting is a problem. So at a certain point, you need to do tuning. And the way you can prevent overfitting with these residuals is by saying, how many trees do I want to fit? Do I want to fit 100 trees or 500 trees? The more trees you do, the more overfitting you're doing. So you need to figure out when to stop fitting. There's a question about the juice function. When we get to the next time we're using juice, I'll talk about juice then. If there's more questions, please ask them. I'll actually take a sip of water right now so you can ask questions before I turn to C5.0. This is an algorithm for fitting either regular trees, a single tree, or boosted trees. This only does classification. It has both a formula interface and an XY interface. If it's a formula, the categorical inputs can be either character or factor, but your outcome must be a factor because it only does classification and it doesn't take strings. If you use the XY interface as the inputs and outputs as separate objects, you can use dense matrices for your X argument, and your outcome must be a factor vector. This handles missing data for us, and it provides a rules-based model. So here, we actually are not going to fit a recipe, so we will come back to what juice does in a little bit. But same formula interface we've seen before. We make sure our status is a factor, and we fit on all the other variables. Trials equals 100 means we have 100 boosting rounds. When we plot this, we get this tree. Now, subtree equals 3. This is for one of the trees. We fit 100 trees, each one learning from the previous trees. And here we have this one subtree. I'm not even sure what this is trying to tell us. Honestly, I've given up trying to interpret this, especially since it's just one of 100 trees. But this actually isn't technically one tree. It's actually a subtree, which represents a bunch of amalgamation of trees. So don't try to interpret this. It's a lost cause. We do get a variable importance plot, but it doesn't really seem like it's doing much. This variable importance plot, it tells us it's the percentage of training samples found in the terminal nodes after a split. It's not so useful for many trees for this package. It's more useful if you were just doing one tree, so it doesn't help us that much here. So I'm just going to brush it under the rug and move along. These are our main tuning parameters. Minimum number of cases. This means that is the smallest number of samples that are needed if you're going to create a split. And trials, which is the number of boosting rounds. I'm just going to brush C5 underneath the rug, and you'll see why in a little bit. There are a few more questions, and I promise I'll get back to juice, and there's a question about that. Does learning rate influence overfitting? Sort of yes, sort of no. Learning rate really controls the rate at which you are learning. And so if you imagine you're dealing with like a convex optimization, it can help you figure out, hey, if you've shot past the minimum of the bowl or if you're inching toward it too slowly. It can help with overfitting by making sure you sort of inch your way there. But I use it as just a way of either slowing down or speeding up the process. There's a question, how can we prevent overfitting? You're looking into global minimum to stop tree death, but you're not so sure. We are going to get to model fitting in a little bit. We will get to parameter tuning. And basically the idea of preventing overfitting is prevent the model of a bunch of different values of different tuning parameters and see which one works best. And we will get to that, okay? I'll show you about how to do that and prevent overfitting. It's just actually a way of you try a bunch of things, see what works best. We will get to that. But before we do, let's turn to the darling of Kaggle competitions, XGBoost. This is what a lot of you are waiting for. This can handle regression, classification, and ranking. And I think it actually can handle a few other types of output variables now, more than just these. This can take an XY interface, inputs and outputs. The X can be either dense or sparse matrix, or even files on disk. The outcome must be 0, 1 for a binary classification. It handles missing values for us. It handles class imbalance for us. And it can also even fit penalized GLM models. It could do a penalized regression for you. And it works in either the CPU or the GPU. It is really cool. I love using this thing on the GPU. So to do this, we need to build up a recipe. We need to turn our outcome variable into a 0-based integer, and we need to convert all of our nominal variables into 0, 1 variables, right? We need to turn them into dummy variables. They need to be converted. So what does juice do? When you create a recipe, you're just defining the feature engineering steps. I want to convert this into an integer. I want to convert these into dummy variables. I want to standardize these variables. It doesn't actually do the work. Juice does the work given the original data set. So whatever you have defined the steps on the original data set, juicing does the work. It subtracts the mean, divides by the standard deviation, converts categoricals into dummy variables. It does all the work. And in this case here, we're making our X variable a sparse matrix of DGC matrix, and our outcome variable Y, our regular matrix, a dense matrix. And then XGBoost has a special object, xgb.dmatrix, and we pass it our input xxg and our output label yxg. And you can see that when XGBoost was built, they were just thinking about classification because they called the output a label, because that's very much a categorical way of thinking rather than the outcome or even the target. I'm not a fan of the naming convention. We then fit our XGBoost model by calling xgb.train. We pass it that combined X and Y matrices. We tell it our objective is a binary logistic. We are going to do 100 rounds of boosting. We are going to just see how well we're performing on our training data set, and I will print out how well we're doing our training error every 10 rounds. And then we can plot this, not with the plot function, but by using the digraphs package. And as you see, the longer we're boosting, the more boosting we are doing, the better we're fitting our model. But that's based on the training data. This is overfitting at a certain point. We would need validation data or cross-validation, which we will see in a little bit how to make this fit better. Actually, we might not be seeing that. If we don't see that, I'll tell you about it. And if we wanted to try to visualize the model, there's a function in XGBoost called xgb.plot.multi.trees. And it tries coming up with one tree that is representative of the 100 trees you fit. And if you look closely at this tree, each of those nodes doesn't have one split. It has 5 splits, which are representative of all the trees. Honestly, I don't think this is that helpful. It's a good attempt, but I can't interpret this. It's too much. Luckily, we have the variable importance plot, and this tells us the fractional contribution of each feature to the model based on the total gain of the corresponding feature splits. Again, it's telling us how much each variable cumulatively has influenced the model, how much it has improved the model. And here we have income, seniority, price, amount. Now, XGBoost has a lot of tuning parameters. N rounds, the number of boosting. In fact, the things you're going to focus on most are the number of boosting rounds, eta, which is your learning rate, max depth, the maximum each tree can get, because typically with boosted trees, you want a bunch of shallow trees that you're stacking on each other, a bunch of stumpy trees that build on each other. Early stopping rounds is one way of saying, hey, if my model hasn't improved on a validation, a held out validation set after a certain number of rounds, let it go, right? Just stop training the model. And subsample, that helps you determine the percentage of rows you want to sample for each tree. That means, hey, if I'm fitting 100 trees, each tree use 70% of the data. That's how you inject some randomness in here. And if you wanted to, you could combine that with num-parallel tree and call sample by tree, and you can fit a boosted pseudo-random forest. That way you're fitting multiple trees in parallel and then doing rounds of boosting for each of these trees in parallel. In my experience, that doesn't gain me much over just doing regular boosting, but the option is there for you and it might work. And we have all these different tuning parameters. The way you prevent overfitting is either through a validation set or a cross-validation, and you try a bunch of different combinations of tuning parameters, and you find out which combination gives you the best predictions overall on your held out validation set or through your averaged cross-validation. We have one more model type to get to. This is lightgbm. It's like XGBoost, but different, and it's put out by Microsoft. This can take regression or classification, and it only has an XY interface, an input-output interface. And just like XGBoost, you can't provide the X and Ys individually. You need to actually provide them into an lgb.dataset object, which is then fed into lightgbm. Your inputs can either be a dense or sparse matrix or files on disk. And categorical inputs can be treated either as dummy variables, or you could encode them numerically. And your outcome variable, if you're doing binary classification, which we're doing today, has to be 0, 1. And the outcome can be either a dense or a sparse matrix, which is really cool. This also handles missing values for us, and it will handle imbalanced data for us. And it will work either on the CPU or the GPU for very fast fitting. The way we use this, we build up a recipe, and we convert all of our nominals into integer-based, zero-based integers. We don't do dummy variables anymore. We then make sure that and actually what we do then is we find out which variables are categorical, right? And we will use that in a little bit. Because remember, we are feeding now a matrix of inputs where we don't have dummy variables, but a single categorical variable is stored as a single column as 0, 1, 2, 3, 4, 5, depending on the number of unique values. We then call lgb.dataset to build up our dataset. We pass it our X matrix, our Y vector or matrix, and we tell the dataset which of the variables in our input matrix are categorical, because lightgbm handles them differently than they would dummy variables. It does a type of new numeric encoding on the categoricals and fits them differently. And then we take our data set, we pass it to the lightgbm function, and we can give it our tuning parameters, like the number of rounds. We tell the objective outcome is a binary, and that it's unbalanced, and it should balance it for us. And it goes through and does 100 rounds, in this case, of boosted trees. If we try to plot the model, it doesn't work. We get an error because there's no model plotting built in, which is probably for the better. But luckily, it comes with a variable importance function built in. And in this case, it uses percent gain and accuracy. In this case, income, seniority, the amount you're asking for your loan, and the price. This has a number of tuning parameters, so many that we are not going to get to them. Just know that you probably want to focus on num iterations, which is the number of boosting rounds, the number of trees to fit. You want to look at the learning rate, how fast this thing should learn. You want to look at max depth, how complicated each underlying tree should get, and bagging fraction and feature fraction. Again, at each tree you're fitting, subsample the rows so you're not using all of the rows, and subsample your columns so you're not actually looking at all the columns for each tree. It injects randomness into the problem. I see there's a question about cross-validation. Cross-validation is a bit more involved to explain, but basically, let's say you're doing 10-fold cross-validation. You're splitting your data set up into 10 discrete folds. You have 1,000 rows, you have 10 sets of data, each of 100 rows. Then what you do, you're going to take 9 of those sets of data, 9 of those sets of rows, 900 rows, fit a model on those 900 rows, and predict on that held out 100 rows, and see how well you did. Now, you take a different subset of 9 folds, a different 900 rows, which are distinct, fit a model, another model, a second model, and predict on the held out 100 rows of data, see how well you did. And now you've done this 10 times. You move through all these 10 sets of data so that each fold, which is 100 rows each, is part of the training set 9 times and part of the testing set 1 time. So you now have 10 measures of a held out validation score. Again, the validation score is you take your model you fit on 9 folds, make predictions on the 10th fold as if it was a validation set, and compute mean squared error, compute log loss, compute accuracy, whatever you want. You now have 9 measures of model fit, and you average them, and that tells you how well your model does. And this is a very common way of evaluating a model by using cross-validation. If you have really large data and a really slow, complex model, some people just use a training data set and a held out validation data set. But if you have a model that fits quickly, cross-validation is actually better than training and validation. And there are many other types of models that we don't have time to talk about today. There's the rule fit model. This actually is a combination of a boosted tree and a penalized regression, essentially fitting a boosted tree like xgboost and taking those as a set of rules and then putting them into a model along with the original predictors and decliminet. It's really cool. There is catboost, which is like lightgbm, but it's put out by Yandex. There's BART, which is for a Bayesian additive regression tree, which is similar to boosted trees, but it's really cool in that it gives you better confidence intervals. And TensorFlow, there's a package called TF Estimators, which has a bunch of pre-canned models, including using TensorFlow to fit a boosted tree. It's really awesome. There's so many of these different interfaces we can look at. You could use a formula, or you could use matrices as your inputs with both dense and sparse, or you could use a data frame as your input with a vector, or you have proprietary formats like xgb.d matrix or lgb.dataset. And your categorical variables can be characters or factors, or dummy variables or numeric encoding. Each package has a different way of doing it. And depending on the package, you have different interfaces. You could have, for rpart, you can have the formula. If you C5 is a formula or a dense matrix. randomForest is a formula or a dense matrix. And it goes on and on. You have all these different ways of doing it. And then how you treat your categorical variables differs by package. XGBoost, you can make them into dummy variables. Like GBM, they can be dummy variables or numeric encoding. Ranger, they can be factors or characters or dummy variables. Too many different interfaces. We want one standard to use all of them. And this will help us with tuning. Actually, we're not going to really see it today, but I'll talk to it briefly when we get to it, that using this one interface, it can handle all of the tuning for us. Actually, we will talk about it. Never mind, we will talk about it. All right. Caret used to be the go-to package for a unified interface for machine learning. But not anymore. Wasn't tidy enough. So now we have tidymodels. This is a collection of underlying packages. which provide a uniform interface to all of these models. And it's funny watching the progression. Caret was written like 15 years ago, and it was great. Then in the Python world, they came up with scikit-learn and pycaret, which were influenced by the original Caret. Now, tidymodels, written by the same author as Caret, Max Kuhn, is sort of been influenced by Caret and by scikit-learn, which came back into R. So we started in R, went to Python, back into R. It's pretty fun. So the first package inside the tidymodels package is parsnip. Get it? Caret and parsnip. So we come here, and if we want to fit a decision tree, one decision tree, we just say, hey, I want a decision tree using classification, and I want to use rpart as the engine for the fitting. If I had wanted instead to use C5 to fit a single tree, I could say decision tree classification, set engine C5. Notice the only difference between these two models was the engine. One engine was C5, one engine was rpart. If I want to do a random forest, I say fit a rand forest for classification and set engine random forest. If I don't want to use random forest, if I want to use ranger, all I have to change is the engine, set it to ranger. If I don't want ranger, actually now if I want to do boosted trees, I say boost tree as my model type. I'm still doing classification, and the engine will be C5.0. Yes, C5.0 earlier did a decision tree, a single tree. Now I'm using it for boosted trees. If I want to use xgboost for my boosted tree, I can say set engine is xgboost. So it's pretty cool the way we can use the same interface and say, hey, use xgboost for this, use C5 for that, use ranger for that. And then if we want to do feature engineering instead of using a different formula for everything, and I will get to the questions, don't worry. We could use recipes to do the feature engineering, but before we do that, we are going to use rsample for splitting up our data. Here we are going to create a training set and a testing set. And that's just general good form when we have our testing set held out for later. We could use a further function validation split to come up with a train, validation, and test, but we don't want that because we want to do cross-validation. Now, unfortunately, each of our different models, rpart, xgboost, ranger, they all expect different feature engineering, different pre-processing. So for rpart, we have to upsample our data, and we need to we'll collapse some of our categorical variables, and nothing else needs to be done. For C5, for a single tree, or even for multiple trees, we need to upsample our data and collapse some of our variables to make it a little simpler. For a random forest, here we need to upsample our data, and we need to make sure all of our categorical variables are factors, and we need to impute our data. So little things have to happen here. Luckily, though, it's the same recipes, the same package for doing all of this. For ranger, we need to upsample our data, we need to do imputation, we need to make sure we have factors. For C5 for boosting, once again, we just need to upsample our data. For xgboost, I'm choosing to upsample here, though I don't need to. I could have had xgboost do this. And I'm converting all my categorical variables into dummy variables. Now, I'll pause for a second for some questions. There's a question, can tidymodels train multi-class instead of binary? Yes, tidymodels can train regression outcomes, binary outcomes, it could train multi-class outcomes, it could train Poisson outcomes, it can do survival outcomes. Then for different types of models, it could do GLMs, decision trees, boosted trees, random forests, Cox proportional hazards, other types of survival models. It can do rule-based models. It can do multi-level models, which is like hierarchical models. It could do generalized additive models. It can do the whole shebang. It's amazing. There's another question about lightgbm. I don't think you have to do pruning of it. I'm not positive. And tree depth was just one of the parameters. I forget exactly which parameter it was. It was like num iterations or num rounds or something like that. There's a question about how do we do an algorithm for selecting hyperparameters? I believe we're going to get to that. If we don't get to that, I will mention it. All right. But back to our model. I know we're running out of time here, so I will continue onwards. Workflows. This is where we're going to put together our feature engineering and our model fitting into one step. We load the package workflows, which is part of tidymodels. And by the way, we could have, to get all these tidymodel packages, I could have just said library of tidymodels, but I like loading the packages individually. It lets me know what I'm doing. I then combined a recipe with a model. So I'm making rpart, taking the rpart recipe and the rpart model, the C5 recipe and the C5 model. For randomForest, I'm combining the randomForest recipe, the randomForest model, the ranger recipe, the ranger model. Same with C5 boosting and XG boosting, okay? I'm putting all of these recipes and models together. That way, when I call fit, when I call like fit on the data set with my model, we'll do all the pre-processing and then do the model fitting. And now it's time to do just that. If we're not doing any hyperparameter tuning, which please hold, we simply say, take our workflow model, which combined our model specification with our feature engineering, and call fit with the model type and our training data. And look how we do this for each of the models. This is fitting 6 different models right here. And that is pretty good. That's really, really cool. Now, I say how cool this is because I don't need to remember, do I use a formula or do I pass in an XY? I don't need to remember, do I use need to have xgb.train or lgb.train or just rpart or rpart.fit. I don't need to remember any of that. I simply have to take my recipe, which is the same way of building it for all the models. I specify the model type using parsnip the same way, and then I call fit. I don't need to remember individual functions. It's really nice. Then we need to see, how do we do for these models? And it looks like I'm not going to get to parameter tuning, but in tidymodels, I'll tell you right now before I go on to the rest of the talk. In tidymodels, there is a package called tune, T-U-N-E. And that provides many different ways to do tuning parameters. Let's say you have 4 tuning parameters. You can fit a random grid where you choose random combinations of tuning parameters and fit your model for each combination and see which combination did the best, either on the held out validation set or on cross validation. And that is how you prevent overfitting also. And that's how you do automatic tuning and prevent overfitting. It also provides other ways of doing searches. For instance, you could do a Bayesian search where you choose one combination of tuning parameters, see how well you did, and then choose your next combination of tuning parameters smartly based on how well your model did. And you keep doing this until you converge. It can also do simulated annealing as a way to find the best. In my experience, I do a random grid, and then maybe I'll use simulated annealing to fine tune that to get a little bit better. And by the way, if you want to do that, first you tune with the tune package, then there's the fine tune package to do the simulated annealing afterwards. So that hopefully answers the questions about overfitting and automatic tuning. There's a question about cat boost. I like the idea of cat boost. I don't like the interface as much as I like base R interfaces. Then again, it's the same interface as xgboost practically, and the same interface as cat. That's not entirely true. Lightgbm and cat boost have very similar interfaces. They're very, very similar. And then they're both inspired by xgboost. The performance is great. The speed is great. But at that point, I'm just using xgboost because it works on the GPU. It's a known entity, and it's just fine. All right, cool. So let's go and evaluate our different models and how well we did for each of them. We're going to look at this in terms of both accuracy and speed. So we are going to put all of our workflow models into a list, and we will iterate over them. We'll fit each one programmatically. Yes, there is a way to do this using a package called workflow sets, but this way worked for me. I then am going to define my quality metric, and since we're doing a binary outcome, I'm going to use AUC as my quality metric. So first, I am going to use this function called last fit. And I'm going to use the per package to map over my model. So for each model, I'm going to fit the data using the training data and see how well I did on the test data. And I'm going to evaluate it using our quality metric. All right. So again, for each of our models, that's what per does. It's going to iterate over those 6 different models. And it is going to say, hey, fit a model using the training data, then make predictions on the test data and report back how well we did. And this is just more code to, after you've done the model fitting, go through and collect everything and put them all together. There's just some boilerplate code to do that. Then we will plot it using, believe it or not, Plotly. Not ggplot with ggplotly, just Plotly directly. And we could see here in terms of accuracy, rpart, the single tree, did the worst. And then Ranger did the best, with xgboost and randomForest coming in closely thereafter. And this will, this will vary depending on your model and even your computer, by the way. Then we also want to see how we did for speed. Now, we didn't compute that yet. So what we are going to do now is we are going to use the bench package, and we are going to use press to apply the mark function to each of our models. That sounds a little bit weird, but basically we are going to fit the model for each of the 6 models and track its time. The bench package is a little bit weird. Mark is how they use to compute how fast something is, but if you want to call mark repeatedly on a list of objects, use press. So again, press means for each element of models, which is our 6 models, do something inside of mark and track the time. When we do that, we get the speed differences. And here, C5 was the fastest. That's actually C5 for a single model was the fastest, followed by rpart, and then xgboost, which does boosting. And the slowest packages was randomForest and Ranger. So what you really want to see, though, you don't care about the most accurate. Maybe you might care about the most accurate by itself or speed by itself. You probably want to see which model gives you the best combination of speed and accuracy. So here, if speed is on the x-axis, you want to be as far to the left as possible. AUC is on the y-axis, you want to be as far to the top as possible. So our goal is to find that Pareto optimum of being near the top left. So going to the top left, we see xgboost for this data set has the best combination of speed and accuracy. So that's what I would use for this problem. This actually is a very common workflow. I would try a bunch of different models with a bunch of different tuning parameters and see which one worked best for this particular data set. So let's do the key takeaways, and I'll give a chance for any questions right now, then I'll do my key takeaways. Do you have any questions about this evaluation we just saw? And I know I went a little faster toward the end there. This talk took a little longer than I expected it to, so I just want to make sure we can get everyone out of here. So that we have giveaways for both books and for conference tickets. So are there genetic algorithms for tuning? It depends what you consider a genetic algorithm. I think I know what you mean. I'm trying to think if tidymodels, I'm just talking about tidymodels here, if tidymodels has genetic tuning. Because I know it does a Bayesian optimization, it does simulated annealing. It might do genetic. I vaguely remember reading that, but I don't know for certain. It might do a genetic algorithm. Don't quote me on that, though. All right, cool. I'll give you my summary overview, and then we can turn into see if there's any last lingering questions. So what I learned from here is that xgboost is the fastest algorithm we could use. And it was the most correct-ish, most correct. And I'm not reading what I'm supposed to be reading to, I apologize. So basically the thing we learned is that there are so many interfaces to know. If you don't want to use tidymodels, you need to know the interface for xgboost, for rpart, for Ranger, for lightgbm. And there are nuances for each of these models. And that from our evaluations here, xgboost was indeed the fastest. And it was nearly the most correct. and that's for this data set on my computer. The important thing to remember is that everything is easier with tidymodels. With tidymodels, you don't need to remember the individual package interfaces. You don't need to worry about by the way, each of these packages uses a different name for each of the tuning parameters. With tidymodels, they use the same name and it translates it for you. And it handles cross-validation for you. And it handles tuning for you, whether you want to use random grid search, Bayesian optimization, or simulated annealing. It handles it all for you. That makes life all a little bit easier to handle. So if you're going to be fitting machine learning, my big message now is to use tidymodels because it has grown a lot in the past 3 months even. It does GLMs, decision trees, random forests, boosted trees. It does survival models, different types of survival models. It does generalized additive models. It does multi-level models. It does so much cool stuff. I highly recommend just going to tidymodels. Plus, you can tell a model to fit natively in your computer, or you can have it use a Spark interface if your data is already in Spark. And hopefully soon one day it could use other database algorithms as well. This thing is really cool, and there's a whole line of putting models into production. We didn't even talk about that. Tidymodels comes of a way of turning your model into an API and wrapping it inside of a Docker container, and then letting people hit that container to get predictions out of your model. It is really, really cool. So with that, I know we spent a lot of time. Thank you very much for being here. And if there's any questions left, I'd be happy to answer them. Then after that, we can dive into the giveaways for both the books and the conference tickets. So thank you very much, everyone, for being here. I really appreciate it.
Yeah, and I'm actually ready for giveaway. If maybe we do that first while people are typing out questions, and then we do questions. So really quick here. So just a reminder that we have 5 ebooks to give away, as well as 1 conference ticket to the 2022 New York Art Conference. If you are a winner today, we will be sharing your information, your contact information, with Jared and his team, and then they will be in touch with how to claim those prizes. So first we'll do the ebooks. So the ebook are for everyone. We have 5 of those, and I really apologize if I butcher your name. So just hang with me. The first winner is Kala Awadi. So you will receive a ebook to the R for Everyone. Nicholas Stumberger is also receiving an ebook. Fidelis Ide, you're receiving an ebook, and Sidone Ade Sedami Dako. You are our last ebook winner, so congratulations to those 5. And then, or I think I forgot Amanda McNeil as well. So there you go. Amanda, Kale, Nicholas, and Sidone, and Fidelis, you are all receiving ebooks for everyone. And then for our New York R conference for 2022, either an in-person or a virtual ticket, Heather Meckler, congratulations on that. You'll receive the New York R conference ticket, and Jared and his team will be in touch with all of you about how to claim the prizes.
Great. Congratulations to everyone who won. I wish I could sign your ebooks, but I can't because no one's invented a way to do that. That'd be really cool. That's what you lose with paper books, without paper books. You lose signatures. But thank you, everyone. And I believe we also have like a discount code we can give everyone for the conference that I believe they're going to send out.
Right. That's one other thing I should have mentioned. When we send out the recording, and in the recording, we'll have a promo code. So if anybody who if they want to attend the conference, use that promo code. And I'm not quite sure what the discount is on it, but I know it's a little discount there for you.
It should be, I believe, 20%. So it's a nice chunk.
That sounds right. Yeah.
Yeah. And I see there's another question here, and I do want to say, I hope I'm allowed to say this, I'm hiring. So if anyone wants to apply for a job, landanalytics.com. It was too late for me not to say it. landanalytics.com/careers. I'm hiring for a multitude of roles, sales roles, data scientists, Shiny developers, Linux admins, the whole thing. So be in touch.
Yeah, Jared, maybe we can have another webinar where you just describe what you're hiring for.
Absolutely. We have a lot of stuff. We do a lot of cool stuff. There was a question about the slides. They're all available at all of my talks, including this one, at jaredlander.com/talks. This one is called Finding the Tallest Tree, something the tallest tree. If you go to jaredlander.com/talks, you will see, search for the word tree, and you will find it there, along with all the other talks I've given. And I think Data Science Dojo might be sending out links and everything.
Yeah, we'll also share the slide deck for this talk specifically in the recording as well.
Great, great. I did see there's a question in the chat. My website's jaredlander.com. My name, well, that's my personal website. If you're looking for the Lander Analytics, it's landeranalytics.com. All right, cool.
All right, I think that's it. So thank you, Jared. Thank you, Nicole. And thank you, everyone, for joining. A special shout out to my team member, Fatima Rafiq, for setting all of this up, doing all the logistics. She works really hard on all of our webinars. So thank you, Fatima. Reminder to the winners, we will share your information with Jared and his team, and they will be in touch with you. We also have another webinar coming up tomorrow morning, 9 a.m. Pacific, bright and early. With the title is ML Ops Crash Course for Beginners. There will be a certificate of attendance with this crash course, and it's being presented by Hamza Tahir. He is a co-creator of Zen ML. So join us tomorrow morning if you're available, and if not, it will be recorded as well. So thank you, everyone. Thanks again, Jared. Thank you, Nicole. Thank you, Fatima. And hope everybody has a good rest of their afternoons.